right. Welcome to the deep dive. Today, we're going to be digging into something that's pretty fundamental. Like when you're thinking about how fast your computer is, this is really at the core of it. We're talking about PCI Express, PCIe for short.
That's right.
Now, you probably already know this, but that's where you plug in things like your graphics card, your super fast SSDs. And we're going to really kind of get into how it actually manages to move so much data so ridiculously quickly by looking at, the kind of structure underneath it all.
Yeah, if you think about the cutting-edge components in a modern computer, PCIe is like the highway system connecting them all.
It is.
It's the backbone of high-bandwidth communication. So understanding how it works, and specifically these layers we're going to talk about, it's not just some geeky engineering stuff. It actually gives you a real insight into how all that data gets from point A to point B so fast.
Yeah, and PCIe wasn't always around. It had to replace some older technologies. Like some of you might remember PCI, PCIX, AGP. They were all trying to solve this problem of how to get data moving faster and faster. But PCIe really was a step change.
It was. And there were a few key reasons for that shift.
Yeah.
You had the need for speed, of course, but also moving to PCIe meant fewer physical pins on the cards, which is great for making things smaller.
Yeah.
And a smaller overall footprint on the motherboard. But fundamentally, PCIe was designed to scale, to handle the kind of performance demands we'd see in the future, which is, where we are now.
Exactly. It was a real architectural leap forward. And you know what? It actually reminds me a little bit of what happened with USB. Remember those old parallel ports, those huge clunky connectors?
Oh, yeah?
And then USB came along, everything became serial. And that's kind of what PCIe did for these high-speed components inside the computer.
That's a good analogy. Those older parallel bus systems, they were running into some pretty fundamental limits.
They were.
Especially something called timing skew. It's a bit tricky to explain, but imagine you're trying to get data to arrive on multiple wires at the same time.
Right.
The faster the data or the longer the wires, the harder it becomes to keep everything perfectly synchronized.
Yeah.
PCIe, being serial, sidesteps that whole issue. It sends data one bit at a time, and it embeds the timing information right in the signal itself. Really elegant solution.
So let's talk about this layered structure. We keep mentioning it, and it's kind of central to how PCIe achieves both this amazing speed and flexibility.
Right. We're talking about the PCIe protocol stack. And for those of you who know a bit about networking, it's got some similarities to the OSI model.
The 7 layers, yeah.
Exactly. Now, PCI keeps things a bit simpler. It's got 3 main layers, the transaction layer, the data link layer, and the physical layer.
So think of it like a really well-organized system. Each layer has a very specific job to do, and they all work together to make sure your data gets where it needs to go quickly and reliably.
And that's exactly what lets PCIe do its thing. It's not just about raw speed. It's about reliable speed.
And what I find really ingenious about this whole layered approach is that it makes the system incredibly modular. You can develop and improve each layer somewhat independently without having to redesign everything else.
That's a key point. It's why we've seen PCIe go through so many generations, getting faster with each one, without needing to reinvent the wheel every time.
Right. And it's not just about speed either.
No.
Each generation has added new features, improved efficiency, better power management, all while maintaining backward compatibility with previous generations.
That's right. It's kind of like, upgrading the engine in your car. You get more horsepower, but the steering wheel still works the same way.
Right. Okay, so let's actually start going through these layers. We'll begin at the top with the transaction layer. This is where the magic happens, in a way.
Well, you could say that. It's the brains of the operation. The transaction layer is the interface between a device, say, your graphics card, and the PCIe bus.
So it's the layer that's actually deciding what needs to be communicated.
Exactly. And one of the key things it does is manage different address spaces. Think of it like different neighborhoods in a city. You've got memory space, which is where your system RAM lives.
The main memory, yeah.
Then you've got I/O space, which is mostly there for compatibility with older devices that still use those traditional input-output ports. And then there's configuration space, which is crucial during boot up because it lets the system figure out what devices are connected and how to configure them.
So the system can say, okay, I've got a graphics card here and NVMe drive there.
Exactly. And finally, there's message space, which is kind of like an internal messaging system for the PCIe bus. It handles things like interrupts, power management commands, and error reporting.
So it's a real mix of communication types going on in this layer.
It is. And it's all managed really efficiently by the transaction layer, using these things called transaction layer packets, or TLPs.
All right, so TLPs are the workhorses of this layer. You also mentioned split transactions. What are those?
Right. So split transactions are a way to make things more efficient.
Yeah.
Imagine, for example, your CPU needs to read some data from your SSD.
Okay.
In a traditional system, it would have to send the request and then just sit there waiting for the data to come back.
Which, at these speeds, even a little bit of waiting can add up.
Exactly. So split transactions solve this. The CPU sends the read request, but then it can go do other things while it's waiting.
It's like being able to multitask.
Precisely. And when the SSD has the data ready, it sends it back as a separate completion transaction. This keeps everything running smoothly without any unnecessary delays.
Makes a lot of sense. And then there's credit-based flow control, which I have to admit sounds a bit like something out of Wall Street.
Well, it kind of is in a way.
Yeah.
Think of it like a system of checks and balances to make sure nobody gets overwhelmed.
Okay.
Each device on the PCIe bus has a certain amount of buffer space, like a little holding area for data.
Right.
So before a device sends data, it has to check with the receiver and say, hey, how much space do you have in your buffer? And the receiver will respond with a certain number of credits, essentially saying, I have this much room available. The sender can then send data only if it has enough credits.
So it's kind of like a reservation system?
Precisely. And this prevents a fast sender from overwhelming a slower receiver. It keeps everything flowing smoothly and reliably.
So these TLPs, they're like the packets of information that get sent around. Can you break down what actually goes inside one of these TLPs?
Sure. So a TLP has a few main parts. First, there's the header.
Okay.
This is like the address label on a package. It tells the PCI system where the data is coming from, where it's going, and what kind of data it is.
Right.
Then there's the optional data payload, which is the actual data being transferred. And finally, there's the optional TLP digest, which is basically a checksum used for error checking.
It's like making sure the package hasn't been tampered with.
Exactly. So let's take a closer look at that header.
Yeah, break it down for us.
Okay, so the header is usually 3 or 4 double words long. Now, a double word is 32 bits. So that's 96 or 128 bits of information packed into the header.
Wow, that's a lot to squeeze in.
It is. It contains all sorts of vital information, like the format, which tells you if there's a data payload and how long the header is. Then there's the type, which identifies what kind of operation this TLP is performing. Is it a memory read, a memory write, an I/O request, or something else?
Okay.
There's the length field, which tells you how big the data payload is, if there is one. And you'll also find things like the requester ID, which identifies the device that sent the TLP, a tag for matching requests and responses, the address or routing information, and attributes, which are like extra settings for the transaction.
So it really is like a super detailed address label telling the PCIe system exactly what to do with this TLP. And you said the data payload is optional.
Yeah, because some TLPs are just for control or signaling purposes. They don't actually carry any user data.
Like those message requests we talked about earlier.
Exactly. But when they're a data payload, it follows immediately after the header.
All right. And then that TLP digest, that's for error checking.
Right. It's formally called an end-to-end CRC or eCRC. It's a 32-bit value calculated by the sender based on the contents of the TLP.
Like a fingerprint of the data.
Pretty much.
Yeah.
The receiver then recalculates the CRC when it receives the TLP. If the two values don't match, it knows something went wrong during transmission, and it can request a retransmission.
Very clever. And it's optional.
It is. Not all devices support eCRC, so if either the sender or the receiver doesn't support it, it just won't be used. It's an extra layer of protection when available, but it's not strictly required.
So now we understand the basic structure of these TLPs. You also mentioned different transaction types. Could you elaborate on those?
Sure. So one of the most common types is the memory request. This is used for accessing your system's main memory, or RAM. There are different subtypes like MR for memory read, MW for memory write, and MRL, which is a special locked read used for certain operations that need to be performed atomically.
Atomically meaning they can't be interrupted.
Exactly. These memory request TLPs are essential for how your CPU and other devices interact with your system's memory.
Then we have I/O requests, which you said are mostly for compatibility with older devices.
Right. I/O requests, or IOR and IOW for read and write respectively, allow PCIe devices to communicate with the legacy I/O ports that are still present in modern systems, even though most modern devices don't use them directly.
Legacy being the polite term for old, right?
That's one way to put it.
Okay. What about configuration requests?
These are crucial during the boot process. Configuration requests like CR0 and CR1 are used by the root complex, usually part of the chipset on your motherboard, to discover and configure all the PCIe devices connected to the system. It's how the system figures out what each device is, what resources it needs, and how to communicate with it.
So it's kind of like taking inventory of all the hardware in your system.
Precisely. And then finally, we have message requests, which are used for various types of in-band signaling. This includes setting interrupts to the CPU, reporting errors, and managing power states. These message request TLPs don't typically carry any user data. They're just for control and communication within the PCIe system itself.
Okay, so lots of different types of transactions happening, all managed by the transaction layer. Now, we've touched on flow control a bit already, but it's obviously pretty important, so maybe we can go a little deeper into how it actually works.
Absolutely. So as we discussed, flow control is all about preventing a fast sender from overwhelming a slower receiver. It's based on this system of credits, where the receiver tells the sender how much buffer space it has available. But the key thing to understand is that it's a dynamic system. It's not just a one-time check.
So it's constantly adjusting.
Exactly. The receiver will send flow control update packets, or FC updates, to the sender whenever it frees up some space in its buffer. This replenishes the sender's supply of credits, allowing it to send more data.
Okay, so it's like a back-and-forth conversation about available space.
Precisely. And there are different types of flow control packets like FCINT1 and FCINT2, which are used for the initial exchange of credit information when the link is first established.
Right.
And there are even separate flow control mechanisms for the header and the data payload of the TLP, allowing for very fine-grained control over the data flow.
Wow, it's really quite sophisticated. And what about virtual channels and traffic classes? You mentioned those earlier.
Right. So these are mechanisms for prioritizing certain types of traffic. A virtual channel, or VC, is like a separate logical lane within the physical PCIe link. Each VC can have its own dedicated resources, like buffer space, and its own independent flow control management.
So it's like having multiple lanes on a highway, each with its own speed limit.
A good analogy. And traffic classes, or TCs, are priority tags that can be attached to TLPs. So a certain transaction can be marked as high priority, for example, and this will influence how it's handled by the PCIe system. These TCs can then be mapped to specific VCs, allowing you to prioritize certain types of traffic over others.
So it's like having an express lane for really important data.
Exactly. And this is really important for achieving good quality of service, or QoS, especially in systems that handle a lot of different types of traffic.
And you mentioned something called shared flow control and FLIT mode for PCIe 6.0. What's that all about?
This is a new feature in PCIe 6.0 that further improves efficiency, especially when you have multiple VCs in use.
Okay.
In earlier PCIe versions, each VC had a fixed amount of buffer space. But with shared flow control, all the active VCs can draw from a common pool of buffer resources. This is much more flexible and makes better use of the available buffer space, especially when the traffic patterns across different VCs are uneven.
It's like a dynamic allocation of resources, making sure everything runs smoothly.
Okay, we've spent quite a bit of time in the transaction layer, and it's clearly where a lot of the intelligence of PCIe resides. But let's move down now to the data link layer. You said this layer is all about ensuring reliable point-to-point communication.
That's right. The data link layer sits between the transaction layer and the physical layer, and its main job is to make sure that the data gets delivered correctly between two directly connected devices. It does this by adding error detection and correction mechanisms, and it uses its own type of packet called a data link layer packet, or DLLP.
Okay, so it's like a quality control checkpoint.
Exactly. One of the key things the data link layer does is add a 32-bit link cyclic redundancy check, or LCRC, to each TLP.
A CRC, that's a checksum, right?
It is. It's a way to verify that the data hasn't been corrupted during transmission. The sender calculates this LCRC based on the contents of the TLP and appends it to the packet. The receiver then performs the same calculation on the received data.
And if the two values don't match, then it knows something went wrong, and it can request a retransmission. This is done using a negative acknowledgement, or NA, DLLP. If the data is received correctly, the receiver sends an acknowledgement, or ACK, DLLP, back to the sender.
So it's a way to automatically catch and correct errors.
Exactly. And to handle these potential retransmissions, the sender keeps a copy of recently sent TLPs in a buffer called the replay buffer. If it receives a NAK, it can just resend the requested TLP from this buffer.
Very efficient. And what about those sequence numbers you mentioned?
Right. The data link layer also adds a sequence number to each TLP. This allows the receiver to make sure that the TLPs arrive in the correct order, and it can also detect and discard any duplicates that might occur due to retransmissions.
So it's like numbering the pages in a book.
A good analogy. And in addition to error handling and sequencing, the data link layer also manages flow control for its own DLLPs, just like the transaction layer does for TLPs. And it also handles signaling to the physical layer for things like power management.
Okay, so it's got a lot of responsibilities. Now let's talk about those DLLPs themselves. What do they look like?
DLLPs are much simpler than TLPs. They have a fixed size of 8 bytes or 64 bits, and there are 4 main types.
Right.
There are the ACK and NAK DLLPs, which we've already discussed. Then there are power management DLLPs, which are used to coordinate power states between devices. And there are flow control DLLPs, which handle the exchange of credit information for flow control. Finally, there are vendor-specific DLLPs, which allow device manufacturers to implement their own custom functionalities.
So it's a fairly streamlined set of packets, each with a specific purpose. And you mentioned special framing symbols.
Yes. To make sure the receiver can properly identify the beginning and end of each DLLP, there are special symbols inserted into the data stream. The start of DLLP packet, or SDP, signals the beginning of a DLLP, and the END symbol marks its end.
Like bookends for each packet.
Precisely. And it's worth emphasizing how effective this combination of LCRC and the ACK-NAK mechanism is for ensuring data integrity. The vast majority of errors that occur during transmission are caught and corrected automatically by the data link layer without any intervention from the higher layers or the software.
So it's a really robust system, and yet you said that newer PCIe generations have added forward error correction, or FEC, at the physical layer. Doesn't that seem a bit redundant?
Not at all. FEC at the physical layer is an additional layer of protection. It works by adding redundant information to the transmitted signal, which allows the receiver to detect and correct certain types of errors without having to request a retransmission from the data link layer.
So it's like having a backup system.
In a way, yes.
Right.
FEC can handle some errors on its own, and the data link layer's mechanisms are still there to catch any errors that FEC might miss. It's a layered approach to error handling, and it becomes increasingly important at the very high speeds of newer PCIe generations.
Okay, so the data link layer really is like a dedicated quality control department, meticulously inspecting every packet and making sure everything arrives in perfect condition.
I like that analogy. It's all about ensuring reliable delivery between directly connected devices.
And now, finally, we reach the bottom layer, the foundation of it all, the physical layer. This is where the abstract ones and zeros become actual electrical signals, right?
Precisely. The physical layer is where the rubber meets the road, so to speak. It defines the electrical and physical characteristics of the PCIe link, everything from the voltage levels to the types of connectors used.
You mentioned lanes earlier. Can you explain exactly what a lane is in the context of PCIe?
Sure. A lane is the fundamental unit of communication in PCIe. It's a single, bidirectional channel that can transmit data in both directions simultaneously.
Full duplex.
Exactly. Each lane consists of 2 pairs of wires, one pair for transmitting data and one pair for receiving data. And these lanes can be grouped together to form wider links, like by 1, by 4, by 8, by 16, and so on.
And the wider the link, the more data it can carry.
Exactly. The number of lanes directly determines the bandwidth of the link. So a by 16 link with 16 lanes has 16 times the bandwidth of a by 1 link.
And you said that the physical layer handles serialization and deserialization.
Yes, that's right. When data comes down from the data link layer, it's still in a parallel format. But to be transmitted over a PCI lane, it has to be converted into a serial stream of bits. That's serialization. And on the receiving end, the process is reversed. The serial stream is converted back into parallel data. That's deserialization. These conversions are done by special circuitry called SerDes, which stands for serializer deserializer.
Okay, so it's all about getting the data into the right format for transmission. And then there's data encoding. Why is that necessary?
Data encoding serves a few purposes. In earlier PCIe generations, an 8B10B encoding scheme was used. This means that every 8 bits of data is converted into a 10-bit symbol. The extra bits are there to help maintain DC balance on the transmission lines, which prevents signal distortion, and to ensure that there are enough transitions in the signal for the receiver to be able to recover the clock signal.
Clock recovery, that sounds important.
It's absolutely crucial. PCIe doesn't transmit a separate clock signal along with the data. The receiver has to be able to extract the clock signal from the data itself, and the encoding scheme helps to ensure that this can be done reliably.
Makes sense. And later PCIe generations moved to different encoding schemes.
They did. From PCIe Gen 3 onwards, A more efficient 128B130B encoding scheme was adopted. This adds less overhead, meaning fewer extra bits are needed for every 128 bits of data. And with PCIe 6.0, we saw the introduction of PM4, which stands for Pulse Amplitude Modulation 4. This is a more advanced signaling technique that allows 2 bits of information to be transmitted per symbol, effectively doubling the data rate for the same signaling frequency.
So it's all about squeezing more data through the same pipes.
You could say that. And all these encoding schemes play a crucial role in ensuring reliable data transmission at these ever-increasing speeds.
Now, you mentioned link training and initialization, and this thing called the link training and status state machine, or LTSSM. That sounds pretty complex.
It is quite involved, but it's a vital part of how PCIe works. The LTSSM is essentially responsible for establishing a working link between 2 PCI devices. It handles things like negotiating the link width, how many lanes will be active, determining the maximum supported speed, and configuring equalization settings to compensate for signal degradation.
So it's like a handshake process.
Exactly. And it happens every time you power on your computer or reset a device. The 2 PCIe ports involved in the connection go through a series of well-defined states, exchanging special packets called ordered sets to make sure they're both on the same page.
And equalization, that's to clean up the signal.
Right. As electrical signals travel over longer distances, especially at high speeds, they tend to get distorted. Equalization techniques like CTLE and DFE are used to compensate for this distortion and ensure that the signal can be reliably received. The LTSSM is responsible for configuring these equalization settings during link training.
And finally, the physical layer is also involved in power management.
It is. The physical layer defines various power states for the PCIe link, allowing it to reduce power consumption when it's idle or experiencing low traffic. These power states are coordinated between the 2 devices using special DLLPs.
So it's not just about speed, it's also about efficiency.
Absolutely.
Now, you mentioned differential signaling earlier. Can you explain why that's so important for PCIe?
Sure. Differential signaling is a technique where data is transmitted as the difference in voltage between 2 wires rather than the absolute voltage on a single wire. This makes the signal much more resistant to noise, which is essential for high-speed communication. Any noise that affects both wires equally is effectively canceled out by the receiver.
So it's like noise-canceling headphones for data.
Exactly.
And PCIe has gone through some incredible speed increases over the years. It's amazing to think that we've gone from 2.5 gigatransfers per second in Gen 1 to potentially 128 GTs in PCIe 7.0.
It's been quite a journey. And as the data rates have increased, so has the importance of things like AC coupling capacitors, which are used to block DC voltage differences between devices and prevent ground loops.
Right. And then there's the whole issue of lane management. You mentioned that the number of lanes in a PCIe connection isn't always fixed?
Yeah, that's right. While a physical PCIe slot might have a certain number of lanes, the actual number of lanes that are active in a particular connection is negotiated during link training. And in some cases, the number of active lanes can even be reduced dynamically if there are signal integrity issues. It's also important to understand that the way lanes are allocated on a motherboard can be quite complex, with lanes being shared between different devices. This is something to keep in mind when you're building a high-performance system, as lane sharing can potentially impact performance.
So knowing your lane configuration is important. And that LTSSM, it really is the unsung hero of PCIe, making sure everything is configured correctly before any data even starts flowing.
I would agree with that. It's a crucial part of the process, and it's something that most users are probably completely unaware of. But without the LTSSM doing its job properly, none of the higher-level communication would be possible.
Well, we've certainly gone deep into the rabbit hole of PCIe today.
We have.
It's amazing how much complexity is hidden beneath something that seems so simple, just plugging in a card.
It is, and it's a testament to the ingenuity of the engineers who designed this system. This layered architecture, with its clear separation of responsibilities, is what allows PCIe to be both incredibly fast and incredibly reliable.
Yeah, and it's fascinating to think about how each layer contributes to the overall functionality.
Absolutely. You've got the transaction layer managing the end-to-end communication and defining the types of data transfers, the data link layer ensuring reliable point-to-point delivery, and the physical layer handling the actual electrical signaling. They all work together seamlessly to make PCIe the high-performance interface that it is.
Okay, so to wrap things up, can you give us a quick recap of the key takeaways from our deep dive into PCIe?
Sure. So the main thing to remember is that PCIe is a layered system. Each layer has its own specific functions and responsibilities, but they all work together to achieve high speed and reliable communication. The transaction layer handles the actual data transfers, the data link layer ensures data integrity, and the physical layer takes care of the electrical signaling. And within each layer, there are numerous mechanisms and techniques that contribute to the overall performance and robustness of PCIe.
And it's not just about understanding the technical details, it's about appreciating how this layered architecture has enabled PCIe to evolve so rapidly over the years, constantly pushing the boundaries of speed and efficiency.
I couldn't agree more. This modular approach, with its clearly defined layers, is what allows engineers to improve different aspects of PCIe independently without having to redesign the entire system every time.
It's an incredible example of engineering elegance. So, as we look to the future, with PCIe 6.0 already here and 7.0 on the horizon, it's clear that the physical layer will continue to push the limits of what's possible in terms of raw speed.
It will.
But I think it's equally exciting to consider how the transaction and data link layers might evolve to take advantage of this increased bandwidth. What new capabilities will they unlock? How will they manage the flow of data in even more complex and demanding systems? These are some of the questions that will shape the future of PCIe, and I, for one, can't wait to see what the next chapter holds.
Me too.
Thanks for taking us on this deep dive.
My pleasure.
And to all our listeners, keep exploring, keep learning, and keep pushing the boundaries of what's possible. Until next time, happy computing.